the first presentation concerns the types of data that we used for GRACE data downscaling. And I will show our approach on the example of the transboundary Bug River Catchment area. This is the area that we conducted machine learning for. And yeah, so there are the first type of data is obviously GRACE, which is the target data. It was used from Center for Space Research, but this data is going to be presented by Justyna in a later presentation. I will focus on the 4 predictors that we used, which is soil moisture storage. It was obtained from a NASA database, and it's a model called GLDAS-NOAA. The next predictor is precipitation. We used a model called EOPS from Copernicus database. Next one is evapotranspiration, and it's a model called Operational Simplified Surface Energy Balance, and it was obtained from United States Geological Survey. And the last predictor was river runoff, and these were in-situ measurements, data points, point data, which we took from the Institute of Meteorology and Water Management. It is a Polish institution, and for Ukraine measuring stations, we used data from Institute of Hydrometeorology. We also have groundwater table measurements, which were used for verification of groundwater storage. I won't focus on that, only the 4 predictors. So I'm going to tell you how to download the data, basically. So for the first one, soil moisture storage, there are going to be links for all of these data. So the first one is from NASA. How do you say that? Website. Yeah, from NASA website. And you have to type in just this phrase, GLDAS-NOAA, which is the model. This is the spatial resolution 0.25 degree. And this is version 2.1. We use that. And when you type in this phrase into the search engine, there's going to be a window. The temporal resolution is 1 month. The data units are kilograms per square meter, and the data type is netcdf4 or a geotiff for just one variable. But when you type in the search engine this phrase, there is going to appear this window where you can get the data. You have to look. There's also 1 degree resolution available, but we used 0.25. When you click on this phrase, then you have this window, and you have 2 options to download the original files, which include all available variables for a chosen period. You can also choose to download only chosen file subsets, and you can pick the data when you the time frame which you want to include, which you want to download, also the region, and you can select the variables that you are interested in. So when you click on chosen variables, there are all of these available. So if you want to minimize your memory, we used only the soil moisture content at 4 levels. So you can choose just to download these. Then you click on Get Data. It's going to appear at the right bottom. And you get this window. These are like 3 I chose. So you just click to download all of this. And you have to log in to get the data. So there's going to appear another window where you have all of these instructions on how to log in. And then you can download the data. The next one is precipitation. We use the database of Copernicus, as I mentioned, and these are EOPS data sets. The variables available are 8, which are included on the slide. And the spatial resolution is 0.1 degree. There's also available 0.25. The temporal resolution is daily. The data units are millimeters, so you don't have to calculate to these units. And the data type is the same as for soil moisture. And there is like a whole base for all of the available versions. For example, you can choose from the latest version, which I highlighted. We chose the 0.1 degree resolution, and these are the short names for these variables I showed earlier. So you choose the RR, for example. But if you want to access smaller chunks of time, then you can click here. And there's a link that's going to appear, and you can choose from smaller chunks of time. So you also then can minimize the memory. And I also included a link for documentation on what this ensemble mean and ensemble spread means. So you can read into that and how they calculated these data. The next one is evapotranspiration. The spatial resolution is 1 kilometer. The temporal resolution is monthly, and the data units are millimeters. Data type is TIFF, and you when you search this link, when you click on this link, there's going to appear this window. We use monthly actual evapotranspiration. And for example, if you want to download a single month, you can download it here, click on data. But if you want to download bigger chunks of time, then you click on download. You choose from here to select product monthly actual evapotranspiration. You can download the data from a specific year, but I discovered that when you click here, there's a whole list of data available, and you can just click in these links, and you can download all the zips from chosen months. For river runoff, if you want to prepare the data for your area, research area, then you have to obtain the data from your institutes or the institutes from the countries you're conducting the research. We obtained the data from Polish Institute of Meteorology and from Ukraine's institute. The data is point data. We chose daily temporal resolution. There's also monthly available, but I'm going to say a few words about how to separate base flow from stream flow. Just a short presentation. So for that, you have to download the daily data. The data units are cubic meters per second, and the data available was text files. And we had to convert the units to millimeters, so it matches the GRACE data. And we converted it with the use of data on the area of specific catchments and the discharge from gauging stations that close a specific river. And we distributed these data across the smaller the catchments included in the whole transboundary catchment of Bug River. And as I mentioned, I'm going to say a few words about how to separate baseflow, which is which corresponds with groundwater storage. And you can, it's important for verification of and comparison of further calculations. And this, you can treat it as a separate part of this presentation, but I'm going to say a few words. I already showed this presentation for the team of Ukraine, but I'm going to condense this so it's not so long. So we calculate the baseflow by using, sorry, I have an open window. I hope you can't hear it. The stream flow is composed of 3 elements, which is surface flow, interflow, and baseflow. And baseflow is corresponds with groundwater drainage and recharge. So the quick outflow, which has a high frequency, is the quick outflow, which concludes overland flow and interflow. And the baseflow is from groundwaters, which is not a high frequency data. It's more smooth. And we want to extract this component by downloading the data on stream flow from a measuring station that closes a river catchment. So I showed this example of Solokia River, which closes the catchment, and you download the data from this point and you analyze it over time. And you have total flow in the river. And now we want to separate the quick flow and the base flow. And there are a few techniques available for that. So this is the idea, that we have total flow, and here we have base flow. So these are a few examples on how to separate on the hydrograph. This is an example from River Elk, the input data for year 2017. This is a total flow of River Elk. This is a method called fixed interval method, and it shows the separation with this method of base flow. This is another method, sliding interval method. You can read it in the documentation and online. I can send you some stuff on it if you want to get into it deeper. I'm just going to get like quickly. The sliding interval method and also local minimum method. There are many more available, but apart from these, there are other methods which use the recursive digital filters that remove this high frequency quick flow signal to derive the low frequency base flow signal. And in our calculations, we used Eckhart filter. So there's an article which I can also send you that describes this method. And there's an application, a program, which is called BFI Plus. It's available freely, so you can download it and just you can try many methods and see how this works. But for Eckhart algorithm, you have to insert 2 unknown parameters, which is BFI max and alpha or A filter parameter, which corresponds to recession constant. Eckhart proposed a formula for this base flow calculation method. So the BFI max parameter is the maximum value of baseflow index, and it represents the long-term ratio of baseflow to total stream flow. and it sets the upper limit on how much of the stream flow can be considered baseflow. And Eckhart conducted an analysis that shown that the BFI parameter has a bigger influence on the results than this other parameter alpha, and it ranges from 0 to 1. It also cannot be calculated or measured, and it is selected based on the characteristics of the catchment that we calculate on. And Eckhart proposed 3 solutions for choosing BFI value, which are described here. I can also send you the presentation if you would like to read into that. And alpha parameter is determined by a recession analysis. You choose from long-term daily streamflow data that we downloaded earlier, which was a period with a local flow wave peak, which drops to a local minimal values before the next rise. And you can try it on few these excerpts of time and data. And you conduct an analysis. I conducted just in Excel, which is very easy, and it's based on Maillet's equation, which is used in hydrogeology for mathematical description of recession curve of springs, and it also can be used here. But when we get the recession coefficient from the Maillet's equation, we have to get the parameter that we insert in the application, we have to just subtract the alpha from 1. And I have also the Excel spreadsheet if you would like to see how this works. I won't be showing here because Tatiana and Justyna are going to show in their presentations. So that's from me. Thank you for your attention. If you have any questions, I will gladly answer. Sorry. If there's no questions, I will just give Justyna the voice.
Okay, hi.
Yeah. One question. Which of these sources is the most time consuming to deal with?
Time consuming?
Yeah.
So maybe Justyna can or Tatiana.
Okay.
Because I only analyzed the data that I downloaded.
Yeah.
So Tatiana and Justyna can say a few words about this. Justyna, how do you think?
So yeah, in general, the higher spatial and temporal resolution, the higher time we need to download the data. But on the other hand, we have data downloaded and we do not have to do anything else with data. But in the case of river runoff, I assume that there are some calculations that should be performed before downscaling of GRACE with this data.
Yes. The river runoff is we're trying right now to maybe better distribute this data. So yeah, you can use many techniques for that.
Yes, yeah, but in general, the global data like GLDAS model with high resolutions are very time and space consuming. So you have to have a lot of space on your computer. So that's one of the problems. But still, so if there are no more questions about data.
Yeah, we also found that we have to have a lot of space. That was the big problem.
I have a quick question.
Yeah.
Did you ever try any of those parameters for ephemeral rivers, or was it always the perennial river?
Are you talking about the baseflow or?
Yeah.
Yes. No, we tried only on the book station, and I also tried in my master thesis. It was also not ephemeral. It was like a normal river. So yeah, we haven't tried on ephemeral. But in
Thanks.
the article, I think they conducted an analysis on many different river types.
Thank you.